Right, so let's begin. Now, here's my an image of my book. This is a book that I published about half a year ago. There's quite a lot at one point in the book about the moon. So now and then in these sessions I'm going to be doing on the full moon and the new moon, I'm going to dip into the book, and that's what I'll do in today's session. Now, it's later on in the book when I talk about the way that the moon seems to show itself in this ground plan of the cathedral here in Wales, which is really the main subject of the book, or at least the use of cosmology in the design of this cathedral. Now, back in 2010, I noticed this relationship here. So you can see the center of the crossing in the cathedral, the center of the chapter house, and then the entrance of the Lady Chapel form what could be called a pyramid triangle. Now, it's a pyramid triangle because it's the type of triangle that you find in a particular type of pyramid. And this particular type of pyramid is the same type of pyramid that is the Great Pyramid in Egypt. And the thing that eventually became apparent, the more I did the research, was that this particular pyramid triangle here is essentially 1/5 of the size of the Great Pyramid. So it has a simple fractional relationship with the size of the Great Pyramid. Now, part of the mythos concerning the Great Pyramid is that it's part of the Egyptians' knowledge, the ancient knowledge of the size of the Earth. And so in this sense, that the Great Pyramid is like a fractional unit of the Earth. Now, this is a very compelling idea, and there's some really interesting research that's been done. And I'll show you a bit by someone called John Michell, who's a very interesting character who was a good friend of my geometry teacher, Professor Keith Critchlow. And he'd give a talk at the Prince's School once a year, which is where I did my MA and where I now teach, or have taught ever since. I did my MA between 2001 and 2003. Now, it was on the equinoctial full moon back in 2010. So it was an equinox and a full moon on the same day, which was September the 23rd. It was also the eve of the feast of Our Lady of Walsingham, which is, I'd just been on a pilgrimage to Walsingham about a month earlier. And in fact, it was the day I got back from the pilgrimage that I found this pyramid triangle relationship. So then around about a month later, on the equinoctial full moon, it struck me that I should probably look at and see whether John Michell's diagram of the Earth and the Moon, which I'm about to show you, if that was actually used in this design, because you can see how the chapter house is in the area where the moon is. So I put the Earth circle in, and I'll describe all of this shortly in a bit more detail, and the moon circle, and then put the moon square in. And sure enough, it fitted really nicely inside the octagonal chapter house. So here is a diagram on the left. This is a diagram that was sort of envisioned by John Michell in around about 1970, I think it was, 1969, 1970. He first showed it in his book, City of Revelation, which was published in 1972, which he wrote in the city of Bath, just down the road from here where I am in Wales. Now, this diagram is really quite remarkable. I'm not going to go into all of the detail of it, but I'll just give some basic details concerning the squaring of the circle. I'm not going to go into the mileage measurements. I do have them on some of my talks on YouTube, so you can look in detail at that. And I might talk about them a bit more at a future session. But because it's a full moon, I thought I'd just sort of explain this diagram. And it's always worth revisiting it if you've already seen it up to now. Right, so here we have an image of two circles whose size relationship is the same as the size of the Earth to the size of the Moon. Now, this relationship, in simple terms, is 11 to 3. Now, the next thing is for the squares to go around these circles. So we now have a square with an edge of 11 and a square with an edge of 3. And the next thing that can go in is what one would call a pyramid triangle. Now, this is that type of triangle that I was talking about earlier as being present in the design of the cathedral here in Wells. It's also in a couple of other cathedrals too, which I'll talk about shortly. Now, this pyramid triangle, it has a base of 11 and a height of 7. And that naturally fits with the size relationship of the Earth to the Moon, because what you have here is the radius of Earth, which is 5.5, and then you have half of the radius of the Moon, which is 1.5. So 1.5 plus 5.5 is 7. Now this is how the triangle actually shows itself within the pyramidal form, the three-dimensional pyramid. And this is the type of pyramid that is the Great Pyramid, the same type of pyramid as the Great Pyramid in Egypt. So as you can see, the square base has edges of 11 and the height is 7. Now, if you were to multiply those two numbers, both of them multiply them by 40, then you end up with the number of Egyptian royal cubits that there are in the Great Pyramid. So the height of the Great Pyramid is 280 Egyptian royal cubits. So that height of 7 is multiplied by 40. And the baseline of 11 around each of its edges of the square is 440 cubits once you've multiplied that 11 by 40. So this fits very nicely with the Great Pyramid itself. Now, the next thing that's going to go in is a circle whose radius is that length of 7. So the height of the pyramid triangle, that becomes the radius of the next circle. Now, there's something significant about this circle in relation to the square, and I'll refer a bit to the session that I did a couple of weeks ago to explain why. Now, a circle with a radius of 7 inevitably has a diameter of 14. Now, if we multiply 14, that diameter of 14 by pi, then we can get the peripheral measurement of that larger circle that's just gone in. Now, when we do that, we end up with this irrational number, 43.9822, and it goes on to an indefinite number of decimal places. Now, 2 weeks ago, when I talked about pi, I talked about 22 over 7 pi. So 22 divided by 7 gives you a very good approximation of pi. So as you can see, the circumference here is divided up into 22. And if you take that unit and you put it along the diameter, you get something very close, but not quite 7. So 22 divided by 7 gives you this close approximation of that relationship of circumference to diameter. Now, this is pi, pure pi, several decimal places. Don't bother reading it. Just take from me, it's an irrational number. So it doesn't go into any sort of fixed repeating rational pattern. With 22 over 7, as I showed you last week, it does go into a pattern. So you can see how it begins 3.14, like pi, but then it goes into this repeating decimal, 142857, 142857, 142857, and so on. So that means it's rational. Now, the way in which this concerns us with what we have here is that if we multiply the 14, so the diameter of that larger circle, if we multiply the 14 by 22 over 7, then we get exactly 44. So 14 multiplied by 3.142857, 142857, and so on equals 44, precisely. Now, the reason why this is significant within this diagram is because the square also has a peripheral measurement of 44. So 11, 22, 33, 44. So this is what's known as the squaring of the circle. Now, there's a whole symbolic dimension to this idea of the squaring of the circle. The circle is heaven, the square is earth. And so the attempt to square the circle is where there's an attempt to bring about a square that has the same peripheral measurement, or sometimes the same area as the circle, but it's seen as being a problem or a difficulty, because it's not actually possible to have a peripheral measurement which is the same, because the circle is irrational or incommensurable in its measure, whereas the square is rational because it's just 1 by 1. So this symbolism of how do we square the circle? How do we bring heaven and earth into relationship? And this is something that's talked about. I was giving a talk the other day and describing how the poet Dante mentions it at the very end of his Divine Comedy, in his way of trying to say, in the way that a geometer attempts to find a square and a circle that have the same peripheral measurement, in the same way Dante tries to describe something which is indescribable, because he's trying to describe the experience he's having or his desire for unity with God. And so he talks about it in relation to that difficulty of trying to square the circle. Now, taking the diagram to its bare bones, this is why this particular type of pyramid triangle works in relation to the squaring of the circle, because as you can see, the radius of the circle comes from the height of the pyramid triangle, like so. And then the edge length of the square comes from the baseline of the triangle. And that's that relationship of 7 to 11. Now I'm going to fade this image back in to this diagram image of Wells Cathedral. So this is how the diagram is seemingly used in the design of the cathedral here in Wells. Now, it does actually happen in 2 other cathedrals as well, which I've included in my book. So all of this is in my book in a lot more detail. York Minster, now this is a particularly interesting example because you can probably see how the chapter house up there at the top of the ground plan is slightly skewed in its orientation. Now, the idea that that would be an unintentional mistake just doesn't really stand up to artistic scrutiny. It's not difficult to align a ground plan. And as you can see, the rest of the ground plan is all very well aligned. So it does immediately suggest that there's something to do with symbolism that's included here. Now, it does appear to be to do with the fact that this diagram also works in the York Minster ground plan too. And this is the reason why. What's known as the inclination of the moon. This is a particular angle of the moon. You can see how this is the orbital plane of the moon around the Earth, whereas this line here is the orbital plane of Earth around the sun. So there's this slight difference. And this is a fact that we know has been known since at least 200 or 300 BC. You don't need modern technology to work it out. So it could have been known for even longer than that. It was worked out by Hipparchus, a Greek astronomer in, think about the 3rd century BC. So you can see that skew there in the chapter house, which appears to be the moon, is the same as this lunar inclination angle. Right, now we're back at Wells Cathedral again with the chapter house here at Wells. Now, as you can see, the chapter house itself is aligned with the rest of the building, but the vestibule that goes into the chapter house from the staircase, that's another one of these skews that's completely unnecessary. There'd be no reason to have a skew of that sort for any practical reason. So one can only assume it's been put there intentionally because everything else is very well aligned. Now, it does so happen, again, that it's at this angle of just over 5 degrees. Now, this is looking up at the vault within the vestibule. What you have on the right here, this is the top of the arch that's coming off the staircase. And then this is the top of the arch that leads into the octagonal part of the chapter house. Now, the other cathedral where it seems to be used, again, it has an octagonal chapter house on the north side of the building. This is Southwell Minster. Has some rather amazing green men in this chapter house. That's one of the things it's most well known for. This area of the cathedral that we're looking at here is a later Gothic addition, and this is where the diagram seems to be used. These 2 pillars here are part of 3 arches that go into the choir. That's where the Gothic work begins, and then the whole of this area is the Gothic area, or the Gothic in style area. The other part of the cathedral is Romanesque, earlier. Now that's exactly where the pyramid triangle goes from in this particular instance. The chapter house isn't skewed in its orientation, and the vestibule that leads into it isn't either. But the doorway, as you can probably see, is off center. Now, there's a photo image that I can show of the doorway here. The doorway is off center on that particular wall, as you can see, and there's one seat on one side, but then there's a doorway taking up the rest of that wall. Now, this pillar in the middle of the doorway is actually at the golden section of this measurement of the wall. So if you take a horizontal measurement like that, this is at what would be called the golden section. To be really accurate, it's actually, if you divided this wall into 13 units, then it would be 8 units to here and another 5 units to here. So it's what's known as a Fibonacci approximation of the golden section. Because the golden section itself isn't based on rational numbers, but this example of this doorway here is. So if we imagine that we take a straight line going east-west through the chapter house, then we take another line that goes to the pillar. So let's do that in this diagram here. So you can see these two lines. One is just running east-west through the building. The other one is going to the pillar, which is between the two doors. And what you end up with, and you can mathematically work this out, that this line here, if it goes to just about an inch off the middle of that pillar, that golden section coincides with the angle that would give you 5.15 degrees, which again is that inclination angle of the moon. So in all three of the chapter houses, there seems to be this angle, but working in a different way in each case. Okay, right, let's start drawing. So I'm going to stop sharing my screen and switch my camera on. Right, now could everyone make sure that they're muted, please? That'd be very useful. Right, what I would do is pin my, if you go onto the image of me and go onto the dots in the top right-hand corner, and you can pin the picture of me to the screen. In fact, actually, I'm going to spotlight for a bit. Okay, right. Okay, right, I'm going to switch my drawing camera on. Now I'm going to work on A4 paper this week. I've got a piece of A3 there, but that's just what I'm going to have in the background. It actually affects the light on my screen. It makes everything, it changes the light setting. So I'm having this white in the background. So I'm only going to work on a piece of A4 like so, and we're going to do a simple drawing of that diagram devised by John Michell, or envisioned by John Michell back in 1970. Right, so first I'm going to turn the paper into landscape, and I'm going to measure 6 inches up from this end of the page, which is going to be the bottom of the page eventually when I turn it back around again. So 6 inches, glasses on. I'm going to make a mark like so there at one end of the paper, and a similar mark down here, both of them 6 inches away from that right side of the page as I currently have it. I'm about to turn the paper back around again. So now I've got that mark there and that mark there. I'm going to turn my paper back around. So obviously both of these are 6 inches up from the bottom of the page. And then I'm going to draw a horizontal line across. Right, the next thing that we need to do is to get a radial measurement. Now this one is 2 3/4 inches. So be very careful about that. Right, if you have A3 paper, what I do is just do it in the middle of the paper. I mean, you could fold your A3 paper in half and then you'd have A4. So that might be the easiest solution. Right, so 2 3/4 inches. Now, to check that you've got 2 3/4 inches, you might as well just put the point of your compasses onto that 2 3/4 inch measurement, and then you should find that your pencil is at 5.5 inches. And if you turn your compasses around the other way, that'll go down to 0. So I'm only saying this because there's various occasions when I've started people off with this 2 3/4 inch measure and they've accidentally done 2.5 inches. So be really careful that you've got 2 3/4 inches. Right, so I'm now going to go into the middle of the page. And draw a circle. So this circle that we're beginning with is the Earth circle, effectively. Right, as you can see, I'm placing the point of the compasses. I'm keeping the same radial measurement, placing the point of the compasses in the, I suppose you could say, the eastern point of the circle, the right-hand point there. And I'm drawing this semicircle here, rather like a crescent moon. Now, this semicircle needs to begin directly below where the point of my compasses was in the paper and end directly above. If it's a little bit too long, that's fine, but we don't want it to be a bit too short. So make sure that if you had a vertical line going through that point there, that you'd be able to go through both ends of that semicircle. Right, having done that, I'm now going to go to the western point of the circle, like so, and do an equivalent crescent moon going the other way. Now, this diagram is sometimes called the three moons because you've got the full moon, the waxing crescent, and the waning crescent. And of course, the fourth face of the moon is hidden because that's the new moon. Right, I'm now going to use these two intersections here. So place the point of the compasses in this one and make a line directly above the top of the circle. And then I'm going to do the equivalent thing here. So what we've essentially done is found, I suppose you could say, the middle path between these two by going up to here, where the two lines cross. That's going to give us a middle line down here. Now, before we do that, we want to do the equivalent move down here too. So directly below the bottom of the circle. So we can now put in this middle path, which will give us north and south, you could say, of our horizon. Right, so now I've established these 2 points on the circumference. We're now going to put two more semicircles in. And this is where you'll see if you've done your initial first two semicircles the right length, because we want to actually have the tip of the petal here, these two petals that we now have. And similarly up here as well. Right, we now have the four corners of the square, which I suppose you could say is the Earth square, in the sense that it's a square that contains the Earth circle, which is that circle we started off with. Now I'm going to do this in a much stronger line, because this is the square which forms part of this squaring of the circle diagram. Right, now if you measure your square, you should find that if you did begin with that 2 3/4 inch measure, you should find that your square has an edge of 5.5 inches. So if you did that, that should be 5.5 inches. And 5.5 is of course half of 11. So what we're doing is working with the pyramid triangle, but in half measures, because you'd need to, it's just easier at this particular size. Right. So bearing in mind that the baseline of the pyramid triangle is 11, so in this case half of 11, so 5.5. So the 7 height would be half of 7, so that's 3.5. So what we're going to do is use the ruler to measure 3.5 inches from the center of the square up to here. Now I'm going to just put a dot there. So from here to here is 3.5 inches. Right, now we can put in the pyramid triangle. So I'm going to again do a strong line along here. This is the diameter of the Earth, as it were, which is the baseline of the pyramid triangle. And then the dot that I made here is going to be the height of the pyramid triangle. So again, I'm doing this in a strong line too. I see that someone hasn't got a square that's 5.5. You'll probably have to go through it again, because you won't end up with a pyramid triangle. This film will go on YouTube again, as with all of these moon sessions that I'm going to do. But if you feel as if you can catch up, then you can start again. Right, now you can see where I'm getting this measurement from here. That's this radial measurement. Now, this is how I'm going to get the moon circle. Now, we only really need to have the moon circle, to be honest. We won't bother putting the square in. Can put the square in, but this is as much as we need, because it gives us that relationship of Earth to moon. Now, as you can see, I'm opening up the compasses again. And in fact, I'm going to open up the compasses to get that height measurement of the pyramid triangle. So this is that measurement of, well, in the diagram, it's a measurement of 7, the height of 7. And you should just cut the corners of the square. Now, the size of this circle here is actually fractionally related to the size of the moon. I won't go into too much detail. It's several million times smaller, but it is actually part of a system of fractional relationship. The moon is 2,160 miles in diameter, or to about 99.97%, and it forms another part of this diagram, which I'll perhaps talk about another time. Like I say, that I have a talk on YouTube where I go into detail with this diagram. But for now, I'll just put some of those numbers on that I was talking about earlier with the squaring of the circle. So first of all, let's just say that the edge of the square is 11. So we have 11, 22, 33, 44. And let's also put that for the baseline of the pyramid triangle. That's also 11 as well, obviously. The height of the triangle is 7. I'm going to put a dotted line in there. Now, the circumference, as I showed you in the slides, that's also 44, the size of that circumference. Right, and I'll put a few details down here with numbers, because it's really good just to get this ingrained in your thoughts, because it really is a remarkable diagram. So the height of the Great Pyramid, if you take that height of 7, 7 times 40 equals 280. That's the amount of Egyptian royal cubits in the height of the Great Pyramid. The baseline of the Great Pyramid is that 11 times 40, giving 440 cubits. Now, as for the squaring of the circle, you remember how this is the circle that we're looking at, has a radius of 7. So let's just say 7 times 2, so that we can get 7 and 7 to get the diameter, equals 14. And then if we go 14 times pi equals, that's 43.9822. It's an irrational number, so it doesn't give us this ideal number that we need for building in units. It is pure pi, but I suppose you could say that for the square to be circled, something needs to happen, something needs to change. So in this sense, the circle needs to be understood rationally, even though it's not. It's an irrational shape. So if we say 14 multiplied by 22 over 7 then we do get exactly 44. So hence we have a circle of 44, pretty much, but not quite. Now, one final thing that I might as well also mention is the angle, 51 degrees and 50 minutes. Now, the angle of the pyramid triangle, there's something really fascinating. I put this in my book as well, in one of the chapters. If we look upon this angle as being a latitude angle, so 51 degrees, 50 minutes latitude, that's actually the precise latitude of where the first manor of land that was given to the Knights Templar. Now, there's obviously so much sort of mythology about the Templars, and interestingly, part of the mythos of the Templars is that they have Egyptian knowledge, such as the dimensions of the Great Pyramid. It's, you know, it sounds a bit random at first, but this is a sort of myth that's come through. Not quite sure where, but it's. I mean, there's traces of it back in the 1800s, so perhaps there is something in it. Who knows? But yeah, so that's the pyramid angle. It actually goes through Woodstock, just north of Oxford. And Geoffrey Chaucer mentions this angle in his treatise on the astrolabe. Now, I won't go any further with that. It's all in the book, so there's a section where I talk about that. Right, so I'm going to share my screen again. So I'll go back to my camera. Go back to sharing my screen. Right, so to finish off with, I'll describe a few upcoming events. Now, there's one that I mentioned a couple of weeks ago. This is a Cosmology pattern drawing course that I'm going to be doing down in Devon, near Totnes. I think it's in the Dartington area. And it's a 2-day course on the 11th and the 12th of November, run by Kairos, which is a charity that was set up by my geometry teacher, Professor Keith Critchlow, and is now run by one of his daughters, Amanda. Now, the sorts of patterns that you do if you come along to the course will be like this. So on the right there, that's a pattern from the Cosmati pavement in Westminster Abbey. And on the left, there's a diagram of it. So it'll be diagrams like that that you draw. Now, the other thing that I want to mention is something which I'm going to be beginning in September next year here in Wales. Now, it's going to be a set of 8 courses that will last for a year, and I'm calling it the Wheel of the Year. Now, it'll be 8 practical sessions. Generally, they'll be 3 days long over a weekend, so you'll need to take one day off, probably a Friday, and a couple of them will also be 4 days long. So when there's a bank holiday Monday, for instance, it will be a bit longer. Now, these 8 sessions, they're going to be on the 8 points of the year. So, for instance, they'll begin at Michaelmas, which is associated with the autumn equinox back in medieval Christianity. All Hallows is then the midpoint between the equinox and the winter solstice, coming up to All Hallows in a few days' time. Now, Christmas is then associated with the solstice. There's a very old idea in Christianity that Christ was conceived at the spring equinox and born at the winter solstice. And then John the Baptist was conceived at the autumn equinox and born at the summer solstice. It's a very early 3rd century document in the church. Now, the 4th session would be Candlemas. That's early February. The 5th one would be around the equinox, around the Feast of the Annunciation. May Day will be the next one. And then St. John in Midsummer, which is around the solstice. And then finally Lammas and Assumption in August. Now, what we do in each one of these courses is draw various sacred geometry patterns, but also we'd do some sort of a craft that would relate to the season that we're in at that time. So, for instance, at Michaelmas, we'd draw an image of St. Michael. On Lady Day, around the equinox, we'd stone carve a green man. That's and the idea of this course is that you begin with the weekend that you're here, but then you perhaps take your work away with you and finish it off in the 6 or 7 week gap between the one that you've just done and the course that you're going to do next. Now, I think we do gilding in the middle of summer, gild an image of the sun. So these are some of the things that we do on this particular course. So it'll be beginning at Michaelmas next year, and I'm proposing that the first course will be from the 27th to the 30th of September, which is a Friday, Saturday, Sunday, Monday. More details will come out about this soon, but I'm just wanting to give a good lead up to it, because it's people will need to put the dates in their diary, and each course will be around about £300, so the whole course will be around 2,500 for the whole year. Right, I hope you've enjoyed this short session today. The next one will be in a couple of weeks for the new moon. And this one, because I am actually doing it at the times of the moons themselves, this one will actually be 9 a.m., so 9 in the morning. Now, if you're unable to come to any of these sessions, they're going to be on YouTube. So, do join me if you can, but if you can't, then you can see it after it's been done. So the next one will be Monday, November the 13th, Monday morning, 9 a.m. And I hope to see you all then. See you next time.